Power in physics or in science is the rate of doing work or of transferring energy. A rate, once again, always means something divided by time. In this case, the most direct definition is power is work over time. W stands for work here, T for time. But work and energy are very closely related. Once again, work is a transfer of energy, so that's the basic same concept. So we could also write power like this. Power is the change in energy, whether it's kinetic or potential, mechanical energy of some sort, over time. Another way to look at power is to break up the first equation. Because work is force times distance, power is force times distance over time. It's a dot product, actually. But let me just ignore that for a second. If you just look at this thing I just circled, or I'll put it in blue right now, d over t, we've heard that before. Well, d over t is velocity. So you could actually write another equation, power equals force times velocity. So these are all closely connected. There's four equations here, but the main one we're going to be using is over here, this one. But all of these can be used. That last one I just wrote, power is force times velocity. That only works if you have a constant force and a constant velocity. I'll just write that down here. The velocity is constant, so is the force. Now, the units for power. Let's go back to the first equation. It's work over time, or energy over time. Well, work is in joules, and then time is in seconds. So work is in, or power is in joules per second. Those are the units. We do have a name for this. This is called a watt. W-A-T-T. Now there's all kinds of issues here because what's the abbreviation for a watt? Well, it's a capital W. That's one of the reasons why I don't like it, because we also use capital W for work, which is a very closely related concept here because it's part of the calculation typically for power. It's work over time. So that can get confusing, but that's what a watt is. So here are some examples. Let's take a look at this problem down here. We have a man carrying a child. I'll try to draw the diagram here. Up a flight of stairs. Here we have the man with a child. Here's the stairs. And what's important here is the vertical displacement of 5 meters. Now the easiest way to do this problem, as with most of them, is to use the power equals the change in energy over time equation. Power is the change in energy. In this case, the energy that's being changed is the GPE. We're assuming they're going up with a fairly steady speed. He's not gaining speed as he goes up the stairs. That wasn't stated, but that's implied here. So the power here is going to be the change in energy, well, the change in GPE. The change in GPE in the time given. Okay, so the power is going to be mg delta h, because the changing h is what changes the GPE over the time. I'll come over here and plug in. The power here is the mass, and he's carrying himself and the child, 95 kilograms. We want kilograms, that's good. We'll use the 10 meters per second squared to make that easy. And the change in height is 5 meters. And the time involved was 20 seconds. Those are all standard units, so when we plug everything in here, that comes out to be 238 watts. Now the question, well, that's part A. That's part A. Part B wants his horsepower, which you may or may not be familiar with. In part B here, it's given that 1 horsepower is 746 watts. So this is just a conversion. In other words, I have 238 watts times 1 horsepower is 746 watts. So 1 over 746. Basically, you're dividing by 746. So you end up with here for the demand 0.32 horsepower for this particular activity, about a third of a horsepower. And as you can guess, the horsepower originally came about by how much work a horse could do in a certain amount of time, and they wanted to rate their devices, specifically the steam engine back at the turn of the century or slightly before. You know, how much work could your steam engine do compared to a horse? A 5 horsepower steam engine could theoretically do as much work as 5 horses, and it improved from there into the future. Second example, here we have a pretty good sports car going from 0 to 16 miles per hour in 3.2 seconds. It's pretty impressive. Alright, so we want to calculate the horsepower required for this. Once again, it's probably best to do power equals the change in energy. In this case, the change in kinetic energy over time. Because the car is not picking up vertical GPE, it's picking up motion, speed, in the form of kinetic energy. Now if you start with 0 kinetic energy, your final kinetic energy is your change. So if I just do 1/2 mv final squared, that is my change in kinetic energy over the time period involved here. So the power is 1/2 times the mass of the car, 1,000, times v final in meters per second, 27, squared, divided by the time of 3.2 seconds, all standard. So it comes out here that P, the power, is, looks pretty impressive here, 114,000 watts, or joules per second. Well, if you convert that to horsepower by dividing by 746, you can just do that on your calculator. I don't need to see the work for that. That comes out to be 154 horsepower, HP, which may or may not seem like a lot, but that's pretty much an average car. The average car in a parking lot is going to be about 130, 40, 50 horsepower. Some cars less, maybe a few more. Some trucks are going to be 180, 200 horsepower, but that's pretty standard. This is a sports car, though, and a lot of sports cars are like 400, 500, 600 horsepower. In reality here, this is the actual horsepower that moves the car. It turns out that in most cases, almost in all cases, about 2/3 of the energy to propel a car or to move a car is lost in heat and friction within the car. In other words, it really takes about 3 times this horsepower to actually move this car, because 2/3 of it gets lost. So this car really is more like about 450 horsepower. You don't need to write that down, or maybe 500 horsepower, because cars are not very efficient. Most of the energy gets lost to friction and heat. So this is actually a pretty powerful car, so to speak, 450 horsepower or more. But according to the calculations, straight up, assuming no losses, 154 horsepower. All right, one more example. All right, third example here. We have a basement that's flooding. I've experienced this personally. So let's look at the side view here. Say here's the basement. And we have water in the basement to a depth of 1.2 meters. That's how deep the water is. And the basement itself is 3.0 meters deep in the ground. And we're going to pump this water out. Now, a couple things we got to be aware of here, and that is, how much water do we have? What volume of water? Well, the volume of water that we have here is going to be the surface area of the floor of the basement times the depth of the water, or call it the height of the water, and that's given here to be, the area is 60 meters squared, we want meters, times the height or depth of the water of 1.2 meters. So the volume of water that we have here is 72 meters cubed. Now we also need to take a look at the density of water, which is given. Now in different books, in chemistry you use capital D for density, but in physics we use the Greek letter rho. The density of water, or the density of anything, is its mass divided by its volume. So this letter on the left here is the Greek letter rho for density. And we're given in this problem that the density of water, which you may or may not know already, is 1,000 kilograms per meters cubed. That's the density, equals the mass divided by the volume of 72. Well, if you do the math here, all right, that comes out to be 72,000 meters cubed of water that has to be pumped out of that basement. All right. Now, once again, the equation that is usually most useful is the power equals the change in energy over time. In this case, though, the water is going to be elevated, so it's going to have a change in GPE, but it's also going to have a change in kinetic energy because the water is not moving, it's just stationary to start with. So we're going to have a change in kinetic energy plus a change in GPE. So there's two types of energy that the water is gaining in the given time period. So the power here, and we're also assuming that the water is being pumped from the very bottom of the basement, from the 3-meter depth. The hose goes to the bottom or to the floor. That results in 1/2 mv final squared, because once again the water starting with a 0 kinetic energy and it's just gaining a speed at the exit point on the ground, plus mg delta h, the change in height of the water over the time. So if we plug all that in, oh, one more thing here, it tells us that the pump itself is 2 horsepower, and that's fine and dandy, but we want to figure out what that is in watts. So basically you multiply by 746, that comes out to be 1,492 watts, making the conversion, and ignoring sig figs for now. So what we're going to have here, back down to this major equation, I'm going to plug into this equation right here. Basically what I have is 1,492 is my power. 1/2 times the mass of the water, which is 72,000 kilograms, times the V final. It tells me in the problem that the water's coming out at 8 meters per second. Don't forget to square that. Plus the mass of the water, 72,000. Sorry about that. That says 72,000 times 10 for gravity, 9.8, times the change in height, which will be 3 meters. I'm going to squeeze that in there. That's mgh over there on the right, all divided by, well, the time, which we don't know. So that's the only thing we don't know. If we move everything around and calculate everything using all the algebra, which you can skip, you can just do that off to the side if you want. But t comes out to be about 2,990 seconds. Okay, what does that mean? And you can leave that as your answer. I prefer to go one more step to give this a little bit more context for me. Divide by 60 to put this in minutes. This comes out to be right around 50 minutes. So that's how long it's going to take to pump all this water out. Almost an hour to pump this water out of the basement.